Let's talk about UI for a minute. First job out of college, I was a front-end web developer, but I really got my start in software engineering by getting into native desktop development. Working with native desktop applications actually helped me develop a mindset to consistently create products that not only make someone's life easier, but we also create code that's maintainable and scalable. And as developers, I feel like we're frequently removed from the end user client. And it's easy to forget who we're coding for. But at the same time, there's a completely different mindset by developing, when it comes to developing software. When you realize that tech is really about the people, it's the people that you make the software for. So I've had a lot of different experiences in the tech industry. Oh my gosh, I have like a very loose wheel. Sorry about that. So I've had a lot of different experiences working across the tech industry. I've seen companies that has run entirely on TDD with absolutely no form of QA whatsoever, and the product did not work. And I've also been in places where there was like absolutely no unit testing whatsoever. So, I mean, there's just like a lot of different scenarios, and these industries, like, I mean, they range from like real estate, 401ks, like all the way to like really niche like consulting software and, down on Groupon. So there's, I mean, what has become apparent to me over the years is the importance of UIs being an increasingly vital component to the success of applications. An application's GUI must create a rich, intuitive, and pleasant user experience. And in addition, you should be able to guarantee the quality assurance of event-driven applications through the active process of exploring an environment. So whenever I talk about software testing, I usually like to refer to this diagram. So what we're looking at is this kind of like pyramid looking thing. We have like unit testing at the bottom and end-to-end testing at the top. And, to the side, there's kind of like this like range between black box testing to white box testing. It's ultimately not necessary to have end-to-end testing for all pieces of your software. And it really depends on how mature the code base is, what resources are available to the team, and so on and so forth. But the foundation of software testing should be, at a minimum, unit testing. And companies with solid code coverage on business logic might be able to have like the bandwidth for, incorporating integration testing. But as long as you like have, your unit testing, I think it's always a great start. But I think a lot of engineers might be familiar with these terms, but what you might be less familiar with is the concept of white box testing and black box testing. So white box tests runs from the runtime perspective. The point is to test how the system functions. And typically, it's developers who end up writing these tests because we know what's in the code. And when we write these tests, we're kind of asking questions like, if we put in an input, do we get out a particular output, and does that output come out every time? And does this algorithm work? And it's a lot easier to like prove mathematically that something works. Black box testing, on the other hand, tests for the behavior and the functionality of a piece of software. And this is done without any knowledge of what's in the code whatsoever. It can be done manually. It can be done by with scripting. And if you haven't had the pleasure of having QA engineers on your team, they're a really, really instrumental process to software development. And if you don't have QAs on your team, chances are you're probably doing the QA yourself, or someone else in your company is doing the QA. It's incredibly important to be able to have humans be able to test the software that you're using. And while it is true that, the upper half of the pyramid has like these particular specialties that maybe only like a quality assurance engineer might be able to achieve, the most successful engineering teams do their best to get the work as close to done as possible before testing and delivery. Okay, so we talked a lot about testing, and I think we should maybe, like, you might be thinking, well, why are we talking about testing? Well, when I got into native desktop development, I actually discovered TornadoFX, and that is, if you're unfamiliar, it's a very small library. It's actually one of my favorite libraries in Kotlin. It was the first one I discovered, and it's a Java FX framework that's leveraged with Kotlin. And I originally joined the community, and I started using it because it was super easy to use. And I realized that TornadoFX allows you to like easily create like very powerful applications because you're harnessing, you know, like the power of your desktop. You have a lot more memory and bandwidth to work with. So I've dabbled with JavaFX for several years prior to that, and once I started using TornadoFX, I just never went back, and it's been a really enjoyable experience. So regardless, when I first discovered TornadoFX, I originally started using it to do things that I didn't want to do. So for example, I was at a company where there were only 3 developers managing 50 plus B2B clients. And on top of that, we had a requirement to create demos that took 1 to 2 hours to reproduce every single time. And I thought, well, maybe we could get some people we could create a GUI so that it can generate some code, and then we don't have to write that code. Eventually I started running into some nasty UI bugs, and you know, we've all run into nasty UI bugs, but what makes them really nasty is that the application doesn't crash. You don't get an error message. You just don't get the behavior that you want. And before this entire thing, I've actually avoided testing pretty extensively because it's not like a super enjoyable topic, right? And so I started asking around. I can't debug this. The only way I can do this is with testing, and the thing is, I don't know how to do UI tests. So I started asking a lot of developers, well, how do you do a UI test? And every single answer I got was totally different. So that ended up leading me to this project where I'm like, okay, well, I don't know how to do it, but what if I could use metaprogramming to be able to kind of figure out like what are the basics, and maybe I can just build off of that. And the idea for the project was simple enough. The idea was that you would be able to upload a TornadoFX project. It would scan and analyze the code, and it would be able to detect UI components like buttons, text fields, and from there generate very, very simple UI tests from that. Okay, so that project was more of a fun exploratory project, but it sparked a whole lot of conversations with my colleagues. I mean, we're talking QA engineers, software engineers, even data scientists. And we talked a little bit about the differences between black box testing and white box testing when it comes to UI testing. Went too fast. Look at that, that mouse is just fighting me. Okay, so I like to consider UI testing a little bit in the middle. It's a bit of a gray area. In particular, with the methodology that I went to create these UI tests for this project, I was using a headless testing framework called TestFX. Although I was writing the project in Kotlin, Kotlin's backward compatibility made it very easy for me to use any Java FX library that I wanted. So, you know, if you haven't given Kotlin a chance, I would definitely recommend looking into it. So the idea of headless testing involves scripting robotic inputs for a particular instance of an application, and TestFX is able to grab the node representing that particular UI element. When it comes to, let's see, oh, I thought I had a slide for that. Just kidding, I do not. But the thing about writing UI tests is it's actually pretty easy. There's only 3 steps. So you have the first one, you need to grab the node that you're looking for. Second one, perform an action with that item. And then the third step is just the robot interacting with the environment, and you have some assertions to check the state of the UI. The idea itself is pretty novel, and so I was kind of surprised to get it working in any capacity. But I kind of got to a point where after I started generating some basic tests, I was like, oh, okay, so we're getting these tests, but they're not very smart. It was still hard not to get excited about the possibilities. Like the fact that I was able to parse out the code at all was just like, that put me back like 3 months in itself. And I'll definitely talk about that later in the talk. But it was really cool to think about how, oh wow, like maybe we could have metaprogramming like help us write UI tests. And some engineers would joke that, oh, you know, like this could like put QA engineers out of a job. And it led to this discussion where it's like, okay, but is it possible to automate testing in a way that really validates the human experience? Oh, we're still with that. Okay, I'll just keep my finger on the mouse. So, can machine learning teach TornadoFX how to write better tests? The point is that testing is meant to be a design activity. There's always going to be like some kind of human component to it. You can never really, truly, completely replace human quality assurance. Automation isn't just intended to replace the work that we're currently meant to do, but it enables us to do our jobs better. TornadoFX-Suite has totally different pools of studies to explore. And I actually went a couple different directions in the last year. I spent a good amount of time looking into AST parsing in the Kotlin compiler, and that turned out to be like an 8-month derivation. But you know, my initial thoughts for this project was to turn to machine learning to create these smarter tests. But for us to be able to use machine learning, we need to know what kind of data we're trying to collect. What kind of generated test maybe passes habitually? Maybe what tests constantly fail? Is there a correlation between the test results and maybe like the application crashes? And the thing is, I think there's a tendency for folks to default to programming as a solution whenever we're presented with a problem. You know, for example, a couple companies ago, I did have like a PM that was like, hey, what do you think about implementing this geolocation feature for this one particular country? And we're like, why do you need this? And he was like, well, we didn't like really tell them we were putting out a prototype. And I'm like, why don't you just communicate that with them rather than having us waste a whole sprint? So, you know, like I think, you know, it's easy to like push the responsibility off to tech, but we really have to like make sure that we're asking ourselves, like when we have a problem that we're looking at, if the solution we're thinking about is really right for the problem that we're trying to solve. Okay, so let's talk about kind of like where that led me to. So I actually did a pretty good amount of research on not just metaprogramming, but the use of TensorFlow, because my original intention was to be able to feed in some data and be able to look at it. And unfortunately, it was not a viable solution. The reality is AI is not very smart. And I like to explain AI to people using like kind of like an episode from Family Guy. So Family Guy, it is an older American TV pop show, but there is a scene where the main character, Peter, realizes that if he tells his boss that he's a smoker, he can get a lot of breaks from work. And Angela immediately goes, "You're not a smoker." So he goes, "Of course I am." And the problem is he like doesn't really know how to smoke. So he starts just trying to move the cigarette to different places and like gauge Angela's reaction. And more or less, that's what AI is. It's the model is your algorithm, and it's going to include these layers and these mechanisms and these weights and biases. You're using Angela to like determine like how close you are to being a smoker, I guess. So, you know, the model is Peter attempting to smoke and Angela using Angela's reaction to gauge the accuracy. So this is like the essence of deep learning, and deep learning becomes machine learning with these successful sequential layers, like hence these tensors. So after all this, I actually went back to some data scientists with all this research, and I'm like, hey, hold up. I don't know if this is going to be right for me because first of all, I actually don't know what I'm looking for. I don't know what makes a good test. And what this led me to is I had to go back to the drawing board and create something far more manual. It was actually a really stupid solution. It's not smart. Metaprogramming is very manual, but I was very surprised to see how well the results worked. So this is kind of where it led me to, where I do believe that for some cases, metaprogramming, neural networking solutions for, in particular, problems that you don't know what you're looking for, it could end up being a little bit more efficient. There's less data required for analysis, and there's fewer unknowns with internal operations when it comes to adjusting data. So let's talk about the differences between neural networking in AI and neural networking and metaprogramming. It's important to be able to distinguish the difference because, it's not very common to hear that it's possible to achieve neural networking with metaprogramming. So for the sake of discussion, neural networking and deep learning and neural networking and metaprogramming is isomorphic to each other. The neural network itself is called the model, but the model is really the algorithm itself. Learning in the context of machine learning describes a process for finding better and more useful representations of data. But how do we know what data is important to us? And I think this actually leads to a whole lot of questions. And, there's actually been a whole lot of talks about questioning AI. And, we have is AI racist? We have everything with Predpool in LA sending police preemptively to Black and brown neighborhoods. We have all these weights and biases, and what just gets to me is that I don't really understand how we could choose what factors of data collection and data mining is useful to us. So that's just kind of the part that kind of gets me. But at least for the sake of this project, I don't even know what I'm looking for. So it's something that it can't work. But neural networking with metaprogramming, on the other hand, actually creates the model itself. In metaprogramming, you must draw these relationships and patterns, and from there, create abstractions from those patterns. Okay, so I started touching on this, but there's a lot of different kinds of problems that you might be able to come across with neural networking. And I did mention earlier that neural networking is not meant to solve everything, and that is so true. In fact, problems for neural networking can be divided into these categories. You have supervised learning and unsupervised learning. Supervised learning includes a target value, and unsupervised learning, of course, does not. So TornadoFX-Suite falls under supervised learning because we don't exactly know what it is that we're looking for. And this supervised learning can be broken down into two different tasks, classification and regression. For classification, the idea is to be able to draw lines to be able to separate the data. Regression draws these lines to describe the data. And for this particular problem, we're trying to locate UI nodes so that we're able to write these tests. We're going to start with the AI locator mechanism and how this problem is popularly solved with very similar things. So the requirement is we need to be able to locate UI nodes so that we can write these UI tests. So there's been quite a few studies and academic papers. I even believe there's some preemptive work released by eBay, and then they kind of took it down recently. But one of the most popular methods for locating UI nodes for classification is an algorithm called convolutional neural networking. And convolutional neural networking is one of the most popular models for being able to generate and recognize these elements. Convolutional layers are just like any other layer in AI, but a convolutional layer will be able to receive transformations from the input in some way, and then the outputs. It's essentially a whole lot of pixel math so that you're able to filter it down. These filters are meant to detect patterns, and this is, I kind of did this animation. It's really a Flash animation, but I thought maybe it's a little bit easier to process how an algorithm works when you just see how it works. So you have these like different kinds of patterns, like we're talking about edges, which is like circles, squares, etc. And then you have these like deep layers, which can detect more sophisticated objects. The filter is a matrix where the value of the matrix is initialized with random numbers. And then that filter, whatever the initialized form is, you know, like in this case, I guess we're looking at like 5 by 6, 6 by 6, I suppose that would make a square. Nope, 5 by 6. Doesn't really matter. But the point is you have all these layers, and you'll notice that we're actually reducing like the details of the filters over time. And you take the max pool of the resulting filters, and the resolution is decreased by 1/2 every single time. Then you take the maximum of every 4 matrices from the resulting filters. And of course, like these dense layers, like means that they have like every single like activation for like max pooling, random weight. There's all this terminology. It's ridiculous. But the point is there's a whole lot of stuff going on. There's a whole lot of really just like matrix multiplication. That's really what AI is. It's just a whole bunch of pixel math, but there's so many at once that we can't really do it in our head. And that's when you feed it through these layers, like that one particular animation was intended to be like one particular layer, one particular filter applied. So you do that a lot more times. Now, let's look at how a locator mechanism might be able to solve the same problem with metaprogramming. As we know, the locator mechanism in metaprogramming is meant to do some kind of classification. So we need to be able to draw lines around the pixel with no knowledge of the code. The issue with AI locator mechanisms is that this methodology does have some weak spots, particularly if you happen to have certain elements that maybe is not in full view. So maybe you have like some floating buttons, like just like sitting over some images, so on and so forth. Or maybe they might be custom elements and they have a very unique design, and it might not be possible for AI to be able to detect those kinds of classifications and draw those lines accurately. Of course, you'd have to feed in a lot more data for that kind of thing. So with these like weaknesses in mind, oh yeah, I guess I have actually a demonstration of kind of like how we might be able to like detect some of these things, but you can see that it might be a little bit difficult to detect the entirety of a scroll view on a single device. All right, so we're going to turn to the metaprogramming locator mechanism, and in particular with TornadoFX-Suite, I ended up taking a white boxed approach that reads the code that we feed in externally at runtime with a library called casttree. It's this obscure library where it's meant to manipulate Kotlin source code as abstract syntax tree objects. And this actually hooks into a portion of the Kotlin compiler, and it draws more or less like the shapes of what Kotlin looks like with, you know, the CFG, context-free grammar, the Kotlin version of that. So an abstract syntax tree is a representation of abstract syntactic structure of the source code, and it's meant to draw lines around the shape of the written language parsed into the intermediate representation of the AST. So, as I said, I don't know what I'm looking for when it comes to finding a test, but I do know what I'm looking for when it comes to locating UI nodes. So for TornadoFX, we have these known elements. We have like buttons, text fields, whatever UI elements like allows people to be able to insert their components. So In our case, the metaprogramming locator mechanism is responsible for locating the UI nodes in the view. So once the AST parser recognizes a view within a project, it's going to dig into those nodes and then kind of like turn them into a directed graph to preserve the hierarchy, oh there we go, the hierarchy of the computer program. So actually here's an example where we have some code here representing TornadoFX, and we have all these like elements right here. And because we have a general AST parser, we're able to feed in some like little plugin or really just a parameter where it feeds in some kind of abstraction for, okay, this is a TornadoFX framework and this is what we're looking for. And it's able to build digraphs that are pretty detailed. So this is actually like very difficult for us to read as humans, but computers can understand this super great. So in our case, actually there's some screenshots of some of the initial breakdowns for some TornadoFX code. So I fed it into the project and it was able to pick up the UI nodes that mattered because you know, it's able to pick up everything in the code and all the UI nodes, but I more or less used a dictionary to pick out the ones that I wanted to write tests for. And then underneath the surface in the logging, this actually held all the references to every element in the diagram. Okay, so we have a animation, and in this animation, oh my gosh. Okay, yeah, in this animation, it's just kind of like a demonstration where the video is a different TornadoFX. It's for a neighborhood cat scheduler. I used it for a workshop to teach people how fun TornadoFX is. And this is like some of the generated code. We dropped like a test into the code. It's a little manual, but then we ran the test, and what's kind of cool about it is you can kind of see TestFX working because you see that headless part. It's trying to fill in the form, and it actually ends up failing. So it's kind of exciting because to be able to get a failing test at all, I mean, in this particular case, we had tied our model to the button, and we ended up discovering like a small UI bug. So, you know, maybe these tests aren't as dumb as I said they were, but they're still pretty simple, but I still think it's a really great start to a lot of different possibilities that we could use for metaprogramming and AST parsing, especially when it comes to generating UI tests. Okay, all right, so we talked a little bit about the comparisons of AI locator mechanisms versus metaprogramming locator mechanisms. And I did do the math, and for convolutional neural networking, the AI locator mechanism, we're looking at mn cubed time versus the metaprogramming locator mechanism at n time, because when it comes to reading the external code with the AST parser, you're really only going through everything once, and you're grabbing and saving the nodes into a digraph structure. Okay, future work for this project is I would actually like to move over to the regression side. It would be nice to continue to follow using like the metaprogrammer. It's not even just like using the metaprogramming locator mechanism, it's actually taking it a step further. We've already built these digraph structures. Let me see if I can get into this. Yeah. So yeah, we in classification, we ended up drawing lines around the dots, but this time we're trying to connect. And with the metaprogramming locator mechanism, it really only functions as one thing, which is just a locator mechanism. But then there's this other aspect to neural networking, which is the ability to make relationships. And because I was able to create these abstract digraphs, we can actually use metaprogramming to try and surmise relations from that. And it can help us answer questions like, how can we increase combination, ooh, it just fell again. How can we increase combinations of permutations of interactions? And what I mean by that is, let's say like we have this form that we talked about in the previous example. And initially, maybe I like wrote I'm going to fill out these things in order. But what if we wanted to be able to write permutations where it's like, I'm only going to input like one input and try to enter the form and see what happens. Or maybe I try to edit something and I had a specific sequence of events. This is the kind of work for QA automation that becomes like really instrumental, because the reality is we do value the human experience, but it's impossible to do all the combinations by ourselves. So this is kind of where I think there's just a lot of different possibilities. Oh, and I actually had 2 ways that I was working on it right before Corona. So there are 2 different ways that I wanted to go into this. So I wanted to create this sense of artificial neural networking with this idea of, I called it abstract compositional contracting. There we go. And so in this case, we can use TornadoFX's class breakdowns and the located UI nodes, there we go, to reanalyze our code analysis to create new graphical relationships, and then remove some of the guesswork of being able to predict the behavior that would come from black box testing. And namely, at the creation of the UI node, we would be able to create this empty digraph and then just create these like functional compositions and associated functions. Yeah, so this is just like some of the future work. Just to recap, there we go. There's some lessons, I think, to learn from this. I think there's a lot of exciting possibilities, but I do want to bring the focus back to, just remembering that using automation can help the tester, but it doesn't necessarily replace the role of the test. Neural networking and metaprogramming is isomorphic to AI and neural networking. I think it's possible to achieve all the components that AI neural networking currently works on with very similar, well, not even similar approaches, just very different approaches in metaprogramming, but it's possible to achieve neural networking as long as you have a definition to work with. And of course, like these models for like regression and classification, when it's done with AI, it can be really expensive and difficult to maintain and wrangle. And honestly, like when it comes to solving problems, you don't really need a sledgehammer for a nail. So make sure that what you're doing is appropriate. You know, like if you have a monolith and you decide to create a bunch of microservices for Kubernetes and you end up creating just like basically a monolith with a lot of more overhead, I mean, that's just like overdoing the solution. So overall, keep it simple. If you're interested in seeing more about the project, there is the TornadoFX-Suite project. Like I said, there's been some distractions, but if you're interested, please feel free to reach out to me on Slack, on Twitter. Actually, that's my information at the bottom. And I do have a good amount of research. If you're curious in hearing more about these observations and research, I did compile some little readmes for data science and also automata. Yep, thank you for your time, and I hope you enjoy the rest of your conference.